All right. So we're trying to model more of the physical properties of light, really switching it up from this pseudo-physics idea of RGB values and moving into this physical reality of light waves and how it works physically. And there's, of course, artistic, intrinsic value in modeling things accurately, but there's also reasons in the sciences, like astronomy and how light interacts with our telescopes, etc., etc.
Now time for some results. You're going to see some beautiful bubbles with really nice spectral highlights and reflections, and you can see that the one on the right has a 500 nanometer wavelength and the one on the left has a 700 nanometer wavelength, and this results in different reflections. And you can see there are like a lot of different bubbles over here. We tried to add a bubble with a solid core inside to see how a thin film would look like on top of a solid object, but due to less number of samples and our machines crashing on higher samples, we weren't able to do that all too well. But this is a scene with bubbles all around. So coming to our technical approach, so for thin films, you basically have a spectral power distribution, and then you also use thin films by calculating a phase shift between a reflected ray at the surface and a reflected ray at the end of the thin film. And based on this, based on constructive or destructive interference, that kind of defines what kind of reflections you'll see on the bubble itself.
Okay, so I wanted to talk a little bit about the technical approach. So for the ray tracer, we implemented a new BSDF. And instead of using a single color, we try to simulate a spectral response. And we do so by sampling a random wavelength and then do this thing called hero sampling, where we get um, specific wavelengths that are on either side of the random wavelength that we sampled. So this is just supposed to decrease noise while also being an unbiased estimator. Um, and then since we don't want to work in just like wavelengths, we want to work in something a little bit more uniform. We end up converting these wavelengths that we sample into this CIE XYZ uniform color space. And then from there, it's just about we're essentially integrating over this. So we want to get the average of all of these wavelengths that we've sampled and then push that into the rendering pipeline.
Okay, so to continue a little bit about the implementation of the ray tracer, the reason that this was done at the evaluation of the BSDF is because by calculating the change in light at the surface of the object, we prevented having to rewrite the entire pipeline to introduce spectral rendering. We isolate the spectral behavior within the BSDF, allowing the rest of the system, light transport, shading, etc., to remain largely unchanged and within our previous framework. Now I'll go through some results. Let's speak for themselves. Before and after with a more zoomed in section, so you can clearly see the effects on the left, a lot more grain, on the right, a lot less. Same for the ball. And in conclusion, understanding light physics is really hard. Probably the most difficult part of this project was just getting to grips with what's going on here, but don't reinvent the wheel. Use the framework that you already have, like we did. That really helped us a lot. And the power of friendship. us all working together with each other is the only reason any of this was possible.